So, hello everyone, I'm Hasini. Today I'll be presenting about the web crippling behavior of web-perforated cold form steel, stainless steel, and aluminum sigma sections. So, as you all know, these cold form sections are widely used in the construction industry, specifically for the low-rise constructions, mid-rise, and modular constructions. Now, these sections are fabricated from different materials, including carbon steel, stainless steel, and aluminum. And also to meet the high industrial demand, these sections are fabricated from an array of sectional geometries. And the cold form sigma sections are one such optimized sectional geometry, which is widely used in the construction industry. So based on this unique sectional geometry, these sections offer a number of advantages over the conventional lip channel sections. So such as the high flexural capacity, high shear capacity, and the cost effectiveness. Now, these sigma sections are often fabricated with web openings to facilitate the easy installation of the service lines. However, these web openings induce the member failure via web crippling under transverse concentrated loading conditions. Yet, no detailed investigations have been conducted on the web crippling response of web-perforated cold form sigma sections, and also no specific design guidelines are available for for predicting their web crippling strength. So, identifying this research gap under the present study, we intend to investigate web crippling response of these cold form steel, stainless steel, and aluminum sigma sections under a combined experimental and numerical investigation. And also, based on the results, we developed unified design guidelines for predicting the web crippling strength of web perforated cold form steel, stainless steel, and cold form aluminum sigma sections under the ITF load case. So here you can see the ITF loading condition. Moving on to the experimental investigation. So initially we fabricated 18 sigma channel sections, basically 6 unperforated sections and 12 perforated sections. So here we considered all the 3 materials and we considered circular centered openings. And to investigate the effect of the opening depth on the web crippling strength, we considered 2 web opening ratios. So initiating the experimental study, we did some tensile coupon tests to identify the material properties of these cold form sigma sections. And here you can see the results of the tensile coupon test analysis. And then we conducted web crippling tests. So you can here see the test setup which we used. And here we considered the unfastened support conditions and we evaluated the effect of the opening diameter and the bearing length. And there we understood that the opening diameter, when we increase the opening diameter, it causes to reduce the web crippling strength. And when we increase the bearing length, it goes to when we increase the opening diameter, it goes to decrease the web crippling strength. And when we increase the bearing length, it goes to increase the web crippling strength. So with that, in order to conduct a more detailed investigation, we developed a finite element model using the Abacus software. And we obtained the material properties from the tensile coupon test and used it in the model. And here you can see the different types of elements and the mesh sizes which were used in the model. And to simulate the contact behavior, we considered the surface-to-surface contact option. And you can see how the loading conditions, how the boundary conditions have been applied via the reference points of the loading and support plates. And the displacement control loading behavior was simulated considering a load rate of 20 millimeters per second. Moving on to the model validation. So after developing the model, we validated it with our own experimental data. So this was conducted under 3 steps. We compared the ultimate web crippling strength values, the load displacement plots, and also the failure modes. Here you can see the model validation for cold form steel and the model validation for cold form stainless steel and the model validation for cold form aluminum. So basically, there was a significant agreement between the results of the the web crippling strength values developed by generated by the finite element model and the web crippling strength values we obtained in the experimental study. Therefore, the model was selected for considering a comprehensive parametric study on the web crippling strength of web perforated cold form steel, stainless steel, and aluminum sigma sections with under the ITF loading condition. So these are the parameters which we considered in our parametric study. So to identify the effect of the section depth, we considered 3 sigma sections. Here you can see the dimensions of those sections. And we also considered the 3 materials, and we considered 2 thickness values. We considered 2 bearing lengths, 2 cone radius values, and also 4 web opening ratios. And to compare the results between the different materials, we considered a unique yield strength value across all 3 materials, that is 220 MPa. And also we considered 450 MPa yield strength to identify the effect of yield strength on the web crippling strength. So basically, considering the ITF loading condition and unfastened support conditions, we developed 480 finite element models. And moving on to the results of our parametric study, in general, we observed that the highest web crippling strength values were observed in the cold form stainless steel sections, and the lowest web crippling strength values were observed in the cold form aluminum section. And when considering about the different parameters, we observed relation between the web crippling strength and opening diameter, section depth, and cone radius. And also a positive correlation was observed between the positive correlation was displayed with the web crippling strength and bearing length, section thickness, and the yield strength. So here you can see how the web crippling strength decreases with the increase of the web opening ratio. So when it comes to larger web opening ratios, there was a significant reduction. And here you can see the effect of section depth. And here you can see how the web crippling strength decreases with the increase of the cone radius and how it increases with the increase of the bearing length. And similarly, here you can see how the web crippling strength varies with the section thickness and the yield strength values. So analyzing the results of the parametric study, we compared those web crippling strength values with the web crippling strength values predicted from the existing design guidelines. So here you can see the design guidelines which were considered under each material. So basically, all the existing design equations tend to overestimate the web crippling capacity of web perforated cold form steel, stainless steel, and aluminum sigma sections under the ITF loading condition. So it was identified that there's a need to develop a new design equation for predicting the web crippling capacity of these sections. So with that, we improved the existing AISI S100 design equation. So here you can see how the equation has been modified over the years to match with the effect of yield strength, then the material properties, and also there have been many researchers to improve this for different sectional geometries. So under this study, we proposed a new reduction factor to so that the equation will be applicable in predicting the web crippling strength of web perforated cold form steel, cold form stainless steel, and cold form aluminum sigma sections under the ITF loading condition. So after developing the equation, we proposed the relevant coefficient values considering the GRG nonlinear solving technique. And here you can see the relevant mean and COV values. And also at the end, we conducted a reliability analysis and developed the capacity reduction factor values for each material. And it was observed that these values were well within the expected range of the relevant codes. And with that, the developed equation was validated for predicting the web crippling strength of web perforated cold form steel, cold form stainless steel, and cold form aluminum sigma sections under the ITF loading condition. So these are the conclusions of our study. So the first study conducted on the web crippling strength of cold form steel, cold form stainless steel, and cold form aluminum sigma sections. So basically the first experimental study on this area. And Based on the results of the combined experimental and numerical investigations, we were able to develop a new design equation, and hopefully with the validation of more research data, we'll be able to include these in the upcoming design guidelines. So that's the end of the presentation. Thank you all for your time.